Good morning, my dear students. So, in this PPT, I am going to explain you about the vectorial representation of an angular motion and the gyroscope couple. Okay, so this gyroscope couple is the derivation will be there. So, in this PPT, this is very important for the point of examination. That is okay. So, already we studied about what you mean by gyroscope effect on naval ship and the plane. So, here I am going to tell you about the how the gyroscope couple we are going to derive the equations. Okay, so now so before going to start the gyroscope couple derivations, or let me understand what this is. Already we studied about what you mean by gyroscope. Okay, so it is a gyroscope is nothing but it is a device consisting of a wheel or a disc mounted. It is a mounted so that it can be spin rapidly about the axis of which is itself free to alter in the direction. Okay, so it is a device which is used to rotate, or which will be spin rapidly about an axis which itself free to alter the in the direction. Okay, the orientation of the axis is not affected by tilting of the mounting. Any of the will be not in the coincident. Okay, so that the gyroscope can be used to provide the stability or maintain a reference direction in a navigation system, automatic pilot and stabilizers, many more. Okay, so this is about the definition of gyroscope. Just to understand that gyroscope is a device or mechanical device which is used to maintain the orientation of the direction. Okay, so in a naval ship, aeroplane, automobile sector, gadgeted electronics component, many more. So this is about the definition of gyroscope. Okay, so again same, this is about the gyroscope picture. Okay, so it is a device which is used to or measure the maintain orientation diagram. Okay, so here the parts of gyroscope are the rotor. The middle part is called as the rotor, spin axis, gyroscope frame, gimbal. Okay, it will work on the angular momentum. Okay, so initial axis of the rotation is conserved and consisting of spin masses on an axle sheet. So this is about the gyroscope device, how it will look. Okay, so now the vectorial representation of angular motion. Okay, to understand the better understand, we should understand this what you mean by angular motion in a vectorial representation. Okay, so let me understand. So we know that the angular acceleration is the rate of change of angular velocity with respect to time. So this already we studied when you are going in PUC also, and the last previous class also. Okay, so it is a vector quantity, and it may be represented by drawing a vector diagram with the help of right hand screw rule. Okay, so here the let us OX is a plane, normal plane, and when you are going to tilt, when you are going to travel some distance, so that will changes OX to X dash, that is O to OX to OX dash. Okay, so same I am going to draw in the vectorial representation in this side. Okay, so consider a disk as shown in the figure A. That is, let us assume a disk, that is a rotated disk, rotating or spinning about the axis, that is OX, known as the axis of the spin, in anti-clockwise direction. Okay, when seen from the front, when if you look at from the front, I shown in the diagram the direction of viewing, the angular velocity in the plane right angles to the paper, normal paper. Okay, so after short interval of time, let me time t, let the disk be a spinning about the new axis of the spin OX dash. Okay, at an angle of t theta, that is a delta theta, with an angular velocity of omega plus delta omega. Okay, so after some time, using the right hand screw rule, initial angular velocity of the disk W is represented by an OX, and the final angular velocity of the disk is denoted by omega plus delta omega, and is represented in vector OX as shown in the diagram shown here. Okay, so here the vector x dash represents the change in angular velocity in the time delta t, that is the angular acceleration of the disk may be noted. Okay, so this may be resolving into two component. One is parallel to the OX and another one is perpendicular to the OX. One is parallel, one more is perpendicular, that is resolving into two forces. Okay, so component of angular acceleration in the direction of OX, we know that alpha t is equal to xr into delta t. So here xr is the value of that the length of the xr is to be taken by or minus ox divided by delta t. So or is nothing but ox dash cos delta theta minus ox divided by delta t. Okay, so here again w plus delta w cos delta theta into minus omega, that is cos delta theta minus omega divided by delta t. So again you simplify this, so you are going to get what w cos delta t plus delta w cos delta theta minus omega divided by delta t. Okay, so here here we are going to get very small delta theta value, so that you can neglect that. Let us assume 1. So alpha t is equal to w plus delta w minus of omega divided by delta t. Okay, so again this plus and minus get negative sign is cancelled, so remaining is alpha t is equal to delta w divided by delta t. So okay, now you apply the limit when delta t is equal to 0. So alpha t is equal to limitation of delta 2 to 0, delta w delta t is equal to d of w is equal to dt. Okay, rate of change of angular velocity is equal to time. Okay, so component of an angular acceleration in the direction perpendicular to the ox direction. Again, similarly what we solved in the previous case, again we are going to solve this. Alpha c is equal to, that is the component of angular acceleration in the perpendicular direction, or rx dash is equal to, that is divided by delta t, same ox dash sin delta theta divided by delta t. Okay, if this is equal to ox dash distance, we are going to get what, w plus delta w sin delta theta divided by delta t. Okay, again you simplify this, you are going to get what, w sin delta theta plus w delta w into sin delta theta divided by delta t. Okay, so again here also delta theta is very very small, neglect. So by substituting delta t is equal to delta t, we have alpha c is equal to, so w delta t plus delta w into delta t divided by delta t is equal to w into delta theta divided by delta t. Okay, so neglect delta w delta t, it is because very small angle. So again you apply the limit delta t is equal to 0. So limit delta t is to 0, w into delta t divided by delta t. Okay, this is equal to w into d theta by dt. So this is equal to omega into omega p. Okay, therefore the total angular acceleration of the disk is given by vector of x dash. Okay, from the diagram, so vector of sum of alpha t into alpha s. So just to substitute the value of alpha t and alpha c, so you are going to get delta w divided by delta t plus omega into delta t divided by delta t. So which is equal to delta w by delta t plus omega into, this is the angular precision, so omega p is equal to precision. Okay, so where delta theta by delta t is the angular velocity of the axis of the spin about a certain axis which is perpendicular to the plane in which the axis of the spin is going to rotate. Okay, so this is about the same I wrote here. So both the diagram. Okay, so as the spin will be there, so same diagram, figure a and figure b from the top, that is the first slide. Okay, so this is about the acceleration. So where delta theta by delta t is an angular velocity of the axis of the spin about a certain axis, so which is perpendicular to the plane in which the axis of the spin is going to rotate, as shown in the diagram. Okay, this angular velocity of the axis of the spin, that is delta theta by delta t, is called as angular velocity of precision. Okay, remember this, what you mean by angular velocity of precision. Okay, and it is denoted by omega p. So this axis about which is the axis of the spin is turn or rotate is known as axis of precision. Okay, so this is also very important. The angular motion of the axis of the spin about the axis of the precision is known as precisional angular motion. Okay, so this is about the vectorial representation of what, this gyroscope. Okay, so angular momentum. Okay, so this is very important. So second part is, and derive an expression for gyroscope couple or torque from the first principle. So first method, that is the direction of changes of omega. Okay, let us assume, let us consider a disk. Okay, disk which is fixed to a shaft which is rotating in a xy direction. Let us assume the disk is rotated at an angle of delta theta, and the speed is same, only direction changes. Okay, speed is same, only direction will be changes, that is a to ab. Okay, that is oa to ob. Okay, as shown in the figure. So here the initial velocity is equal to oa, that is omega, final velocity ob is equal to w. Therefore the change of velocity is equal to what, final minus initial velocity, that is ab is equal to ob minus oa. So you need to calculate ab is equal to what. So from the triangle OAB, sin d theta is equal to, you can use the formula of sin theta, so AB by OB. So AB is equal to OB into sin d theta. So but here sin d theta is equal to very small, neglect. So here AB is equal to OB into d theta. That is called as change of angular velocity. Okay, we know that the angular acceleration alpha is equal to change in velocity divided by time. Therefore alpha is equal to what, change in velocity AB, that is what, OB into d theta divided by time is equal to dt. So again you re-simplify this, OB is equal to d theta by dt. So again OB is nothing but angular velocity omega, substitute d theta by dt. Okay, so gyroscope couple on torque is equal to, we know that the moment, mass of moment of inertia into this angular acceleration. So I as it is, this angular acceleration is equal to what, omega divided by d theta into d theta. Okay, so just to be substitute, g is equal to gyroscope couple is equal to I into omega p. So this is where omega p is an angular velocity of the rotating axis of the precision. So this is an expression for gyroscope couple. Okay, this is very very important formula for in this gyroscope problem. Okay, g is equal to I into omega p. While solving the problem, this equation I am going to use directly. So remember this, and this derivation is also very important for the point of examination. Okay, so just to remember that here g is equal to I into omega p. I is nothing but what mass moment of inertia, omega is equal to angular velocity. So omega p is equal to angular velocity of the rotating axis of the precision. Okay, g is equal to I omega omega p, you have to remember or by heart it. Okay, so while solving the problem you are going to use direct. Okay, so also Gyroscope couple or torque is equal to g into mass of moment of inertia into acceleration, that also you have to remember sometime. If in terms of mass of momentum given means use that formula, otherwise normal 90% we are going to use this formula. Okay, so I hope you understand this two derivations. Thank you very much.